our planet, a blue marble spinning in the vastness of space. From above, it's a mesmerizing dance of swirling clouds and vast oceans. But beneath the surface of these oceans, a hidden force is constantly at work: ocean currents. These currents, vast rivers of water flowing within the sea, are the lifeblood of our planet. They carry nutrients, heat, and life itself across incredible distances, shaping our world in ways we are only beginning to understand. Imagine the ocean as our planet's circulatory system, and the currents as its arteries and veins. Just as our blood carries vital oxygen and nutrients throughout our bodies, ocean currents transport heat, salt, and essential elements across the globe. These currents are driven by a complex interplay of forces: the wind, the sun's energy, the Earth's rotation, and the very shape of the ocean basins themselves. These currents are not merely localized phenomena. They weave an intricate web of interconnected waterways that span the entire planet. From the warm surface currents that bathe tropical shores, to the cold, deep currents that flow silently in the abyss, each plays a crucial role in maintaining the delicate balance of life on Earth. Understanding these currents, their movements, and their influence is essential for comprehending the very nature of our planet. Ocean currents are broadly categorized into two main types: surface currents and deep water currents. Surface currents, as their name suggests, are driven by the wind. As the wind blows across the ocean's surface, it drags the water along with it, creating these vast, slow-moving rivers within the sea. These surface currents are responsible for many of the ocean's most dramatic features, such as swirling gyres and powerful upwellings. Deep water currents, on the other hand, are driven by differences in water density. These density differences are primarily caused by variations in temperature and salinity. Cold, salty water is denser than warm, fresh water, and this density differential creates a slow, deep ocean circulation system known as thermohaline circulation. This global conveyor belt of water plays a vital role in distributing heat around the planet and influencing long-term climate patterns. These two types of currents, surface and deep water, are not isolated systems. They interact and influence each other in complex ways, creating the intricate tapestry of ocean circulation we see today. For instance, in certain regions, warm surface currents can cool and sink, feeding into the deep water circulation system. Conversely, deep water currents can rise to the surface in a process known as upwelling, bringing nutrient-rich waters from the depths. Ocean currents act as unseen superhighways, transporting not only water but also heat, nutrients, and marine life across vast distances. These currents play a crucial role in regulating our planet's climate, influencing weather patterns, and supporting diverse ecosystems. Understanding these currents is essential for comprehending the interconnectedness of our planet and the delicate balance that sustains life on Earth. These currents, driven by the forces of nature, are a testament to the power and complexity of our planet's systems. As we delve deeper into the world of ocean currents, we will uncover their profound influence on our climate, marine life, and even our own human activities. Join us as we embark on this journey of exploration, unveiling the secrets of these unseen superhighways. Surface currents, the top layer of the ocean's circulation, are driven by the ceaseless dance between wind and water. As wind sweeps across the ocean, it exerts a dragging force on the water's surface, setting it in motion. This interaction creates currents that flow in the same direction as the prevailing winds. These currents are influenced by the Earth's rotation, ocean basins, and land masses. The Earth's rotation shapes the direction of surface currents. The Coriolis effect deflects currents to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection causes currents to curve as they flow. Imagine a giant hand guiding these currents into swirling patterns. Continents also shape the flow of surface currents. Like a river guided by its banks, ocean currents are channeled by continents. When a current encounters a landmass, it changes direction, splitting or flowing along the coastline. This interaction creates complex circulation patterns around continents and islands. Wind-driven surface currents, sculpted by the Earth's rotation and continents, create a dynamic tapestry of motion. These currents shape our planet's climate, transporting heat and nutrients across vast distances. Among the most prominent features of surface circulation are the gyres, massive systems of rotating currents that spiral across the ocean basins. These colossal whirlpools, driven by wind patterns and the Coriolis effect, redistribute heat from the tropics towards the poles. Imagine a giant spoon stirring the ocean, drawing warm water from the equator towards higher latitudes. There are 5 major ocean gyres: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. Each gyre rotates clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. These gyres, spanning thousands of kilometers, are crucial for regulating Earth's climate and supporting marine ecosystems. While surface currents are driven by the wind, deep water currents are powered by a more subtle force: differences in water density. This density-driven circulation, known as thermohaline circulation, is a slow, global conveyor belt that plays a vital role in distributing heat around the planet and influencing long-term climate patterns. Imagine a vast, interconnected network of underwater rivers, silently flowing through the depths of the ocean, carrying heat and nutrients across the globe. Thermohaline circulation is driven by variations in temperature and salinity, both of which affect the density of seawater. Cold, salty water is denser than warm, fresh water, and this density differential creates a slow, deep ocean circulation system. In the North Atlantic, for instance, cold, salty water sinks to the ocean floor, forming a deep water current that flows southward. This sinking process, known as deep water formation, is a crucial driver of the global thermohaline circulation. As this deep water current flows southward, it is gradually warmed and freshened through mixing with surrounding waters. Eventually, it rises to the surface in other regions of the ocean, such as the Indian and Pacific Oceans, in a process known as upwelling. This upwelling brings nutrient-rich deep water to the surface, supporting marine ecosystems and influencing primary productivity. Upwelling, the process by which deep nutrient-rich water rises to the surface, is a vital component of ocean circulation and a key driver of marine productivity. Imagine a hidden oasis in the vast desert of the open ocean, where a constant supply of nutrients fuels an abundance of life. Upwelling zones, often found along coastlines and in areas where winds push surface water away from the shore, are these oases of productivity, teeming with life. As surface water is driven away from the coast by winds or other forces, cold, nutrient-rich water from the depths rises to replace it. This upward movement of water brings with it a wealth of nutrients, such as nitrates and phosphates, that are essential for phytoplankton growth. Phytoplankton, microscopic algae that form the base of the marine food web, thrive in these nutrient-rich waters, fueling a cascade of life from tiny zooplankton to large whales. Upwelling zones are among the most productive fishing grounds in the world, supporting a diverse array of commercially valuable species. From the sardine fisheries off the coast of Peru to the salmon runs in the Pacific Northwest, upwelling plays a crucial role in sustaining human populations and economies. These regions of abundant life are a testament to the interconnectedness of ocean circulation, nutrient cycling, and marine ecosystems. However, the intensity and location of upwelling zones can vary significantly due to changes in wind patterns, ocean currents, and climate variability. Understanding these fluctuations is crucial for managing fisheries sustainably and predicting the impacts of climate change on marine ecosystems. The fate of these productive regions and the countless species that rely on them is inextricably linked to the health and stability of the global ocean. The ocean, a vast expanse of water covering over 70% of our planet's surface, plays a crucial role in regulating Earth's climate. Like a giant heat sink, It absorbs and distributes solar radiation, moderating temperatures and creating a more habitable planet. At the heart of this climate regulation system are ocean currents, the ceaseless rivers of water that transport heat from the tropics towards the poles. Imagine the Earth as a giant engine, with the sun providing the energy and the ocean acting as the coolant, preventing overheating. Solar radiation is most intense at the equator, where the sun's rays strike the Earth's surface more directly. Ocean currents, driven by wind and density differences, act like a global distribution network, carrying this excess heat from the tropics towards higher latitudes. This heat transport is not a one-way street. Cold currents, originating in the polar regions, flow towards the equator, bringing cooler water and helping to moderate temperatures in the tropics. This continuous exchange of heat between the tropics and the poles, facilitated by ocean currents, helps to maintain a more balanced global climate, preventing extreme temperature swings and creating conditions suitable for life. The ocean's capacity to absorb and store heat is immense. In fact, the top few meters of the ocean hold more heat than the entire atmosphere. This thermal inertia of the ocean helps to buffer against rapid temperature changes, making our climate more stable and predictable. However, this buffering capacity is not infinite, and the ocean is already showing signs of warming due to human-induced climate change. Deep beneath the surface lies the Thermohaline Circulation, or the Great Ocean Conveyor Belt. This network of currents regulates Earth's climate by transporting heat and influencing weather patterns. Imagine a giant plumbing system circulating water and nutrients across the ocean. Driven by temperature and salinity, warm currents cool and sink near the poles. This process, called deep water formation, occurs in the North Atlantic and Southern Oceans. The cold, dense water flows towards the equator, forming deep water currents. These currents eventually rise, bringing nutrient-rich waters to the surface. Acting like a conveyor belt, this system transports heat and nutrients globally. It plays a crucial role in regulating Earth's climate. Without it, the tropics would be hotter and the poles colder. Climate change threatens this system, with melting glaciers altering salinity and circulation patterns. In the vast expanse of the Pacific Ocean, a climate pattern known as the El Niño Southern Oscillation, or ENSO, exerts a powerful influence on weather patterns across the globe. This cyclical warming and cooling of the central and eastern tropical Pacific Ocean, characterized by shifts in winds, ocean currents, and air pressure, can have far-reaching consequences, from droughts in Australia to floods in South America. El Niño, the warm phase of ENSO, is characterized by unusually warm surface waters in the central and eastern Pacific Ocean. This warming disrupts the normal atmospheric circulation patterns, weakening the trade winds that typically blow from east to west across the Pacific. As a result, the warm water that normally accumulates in the western Pacific spreads eastward, altering weather patterns across the globe. La Niña, the cool phase of ENSO, is characterized by unusually cool surface waters in the central and eastern Pacific Ocean. During La Niña events, the trade winds strengthen, pushing warm water westward and intensifying the upwelling of cold, nutrient-rich water off the coast of South America. These changes in ocean temperatures and circulation patterns also have significant impacts on weather patterns around the world. El Niño and La Niña events typically occur every 2 to 7 years, but their frequency and intensity can vary. These climate patterns, driven by complex interactions between the ocean and the atmosphere, are a testament to the interconnectedness of our planet's systems. Understanding these patterns is crucial for predicting and mitigating the impacts of climate variability on human societies and ecosystems. As our planet warms, the delicate balance of ocean currents is being disrupted. The melting of glaciers adds fresh water to the ocean, potentially altering the thermohaline circulation. Warmer waters contribute to sea level rise and threaten marine life. Understanding these changes is crucial for adapting to a changing climate. The ocean teems with life, intricately linked to ocean currents. Currents transport nutrients and marine organisms, shaping ecosystems. Plankton drift with currents, forming the base of the marine food web. Fish and other species rely on currents for migration and finding food. Marine animals embark on epic migrations, guided by ocean currents. Humpback whales travel thousands of kilometers, timed with seasonal currents. Sea turtles navigate using currents to reach breeding grounds. Even smaller organisms follow currents to areas of high food abundance. Upwelling creates oases of productivity, supporting marine life. Nutrient-rich waters fuel the growth of phytoplankton, the base of the food web. Upwelling zones are among the most productive fishing grounds. Climate variability and human activities can impact these vital ecosystems. Ocean currents are impacted by human activities like climate change and pollution. Melting glaciers add fresh water, potentially altering thermohaline circulation. Ocean acidification and overfishing threaten marine ecosystems. Understanding these impacts is crucial for the health of our oceans. Ocean currents have shaped shipping routes for centuries. Modern technology optimizes routes, saving time and fuel. Currents play a crucial role in maritime safety. Climate change may alter currents, impacting global shipping. Ocean currents shape the distribution of marine life, supporting global food security. Upwelling zones create fertile fishing grounds. Millions depend on these ecosystems for their livelihoods. Overfishing, pollution, and climate change threaten these vital areas. Ocean currents influence Earth's climate and weather patterns. Understanding currents is essential for accurate weather forecasting. ENSO events disrupt atmospheric circulation, affecting global weather. Monitoring currents helps predict El Niño and La Niña events. Ocean currents offer a potential source of renewable energy. Devices harness kinetic energy from currents to generate electricity. Ocean current energy is consistent and reliable. This technology holds promise for a sustainable future. Ocean currents are the lifeblood of our planet. They transport heat, nutrients, and marine life across vast distances. Human activities are impacting these delicate systems. Understanding currents is crucial for the health of marine ecosystems. Section 2. Guardians of the Flow. The future of our oceans, and indeed our planet, depends on our ability to protect these vital currents. By reducing our reliance on fossil fuels, we can mitigate the impacts of climate change, including ocean warming, acidification, and sea level rise. By implementing sustainable fishing practices, we can ensure that fish stocks are managed responsibly, allowing future generations to benefit from the ocean's bounty. We must also continue to invest in scientific research to better understand ocean currents, their interactions with the atmosphere and marine life, and their responses to a changing climate. This knowledge will be essential for developing effective conservation strategies and ensuring the long-term health of our oceans. The ocean is a shared resource, and its protection requires a global effort. By working together, across borders and disciplines, we can become guardians of the flow, ensuring that ocean currents continue to sustain life on Earth for generations to come. The fate of our oceans and our planet is in our hands.